Hi folks, welcome to AP Calculus Chapter 5. We're going to finish up this chapter since we've had so many snow days. We need to catch up with this last method. We're going to do the inverse trig functions, the integration of them. So first of all, take a few minutes and jot these three formulas down in your notes. So you can pause the video and then come back and restart it again when you've copied these into your notebook. You'll notice for these three formulas that they're in terms of two different variables, u and a. For all of these formulas, we're going to see that u stands for the variable part, and a is actually going to be a constant value, so it's going to be a number. So we see that we have three different formulas this time. When we did derivatives, there were 6 formulas, only because they matched in pairs, only differing by a negative sign. When we're dealing with integration, we only focus on the 3 positive ones. So you'll notice that the forms look very similar to when we took the derivative. Look at the 3 pieces, especially in the denominators. When we have the square root of a squared minus u squared, so a number squared minus a variable squared, that's going to lead us to believe that we have an inverse sign or an arc sign. When we have no radical, but instead a squared plus u squared, notice that this is the only formula that has a sum in the denominator, then it's going to show us that we have the form for arctangent. And the last one is going to have a little bit extra. First of all, underneath the square root sign, we're going to see the variable squared first, minus the number squared. But also out in front, we're going to have the variable in front of the radical. That's going to be the form for arcsecant. In the arc sign, we only use the u over a after the arc sign, so the argument of the inverse trig function. But the arctangent and the arcsecant both begin with a coefficient of 1 over a. So we'll see that added to some of our answers. So what I'd like to do is just go through a few examples of these inverse trig integrals with you, so that then you'll be able to practice on your own and continue with review on Thursday. So for our first example, we're going to take the antiderivative of dx over the square root of 4 minus x squared. Now, just to clarify, some people might look at this and think, is it just a u substitution problem? If this were a u substitution problem, I would attempt to make u be equal to 4 minus x squared. But if I tried that, then the derivative of 4 minus x squared would be negative 2x, and that's not present in the original problem. Nor can I multiply by that negative 2x because it contains a variable. So that tells me I've got to use a different method, not u substitution. So this is one of our really, really specialized tools, and I've got to recognize when to use it. So I'm going to identify the pieces here, and I'm going to say, okay, I have a number that's squared, so I'm going to call that a squared. If a squared is equal to 4, that tells us that a must be equal to 2. The second part I'm going to look at is the variable. That's going to be our u squared part of our formula. So u squared must be, in this example, equal to x squared. Taking the square root on both sides, I see that just means that u is equal to x. But the one thing that we have to make sure of is that we then take the derivative. So the du would be equal to 1 dx. And I do have a 1 dx in my original problem. So my general form of this formula is just going to be the one that looks like this. Du over the square root of a squared minus u squared. Now that, of course, we know gives us the answer for arc sine of u over a, so that's just the formula that we're using. When I apply it to this problem, the answer is going to turn out to be the arc sine of my u, which is x, over my a, which is 2. This is an indefinite integral, so we're going to add a plus c. Again, you'll notice that the arc sign does not have a coefficient. So that is our final answer for this antiderivative. So obviously, once we can recognize the formulas, and once we've got these three formulas memorized, these problems are not too difficult to do. Go ahead and write down our second example. This one's a definite integral, so I've got the antiderivative from 0 to 1 of dx over 1 plus x squared. So I just make a quick check here and say, can I do a u substitution? Trying to do a u substitution, I would let u be equal to 1 plus x squared. But the derivative of 1 plus x squared is 2x dx, and I don't have a 2x dx, nor can I multiply by it. So instead, I'm going to use this new method. The only way that I can solve this is by using my inverse trig. So again, I identify the pieces and I say, oh, this one looks like it's got no square root in the denominator. So that leads me to believe that I've got the formula for 1 over a times, in this case, it's going to be an arc tangent. You can also write tan inverse of u over a plus c. This one won't have the plus c because I know that it's a definite integral. So in this case, the a squared is equal to 1, so that tells me that a must be 1. The variable u squared is equal to x squared, so u must be x, and therefore the derivative of u is just 1 dx, which I do have. So filling everything into my formula, in this case I'm going to have 1 over a, so 1 over 1, times the arc tangent of u, which is x, over 1. I'm not going to put the plus c because it's a definite integral. So this is just the arc tangent of x evaluated at 1 and at 0. Now just remembering how we evaluate inverse trig functions, we're going to say the arc tangent of 1 minus the arc tangent of 0. Now we have to be pretty good at evaluating these. We want to know what angle gives us a tangent of 1. In degrees, that's going to be 45 degrees, but I always have to give this answer in radians, so it's going to be pi over 4. What angle gives me a tangent of 0? That answer is going to be 0. So when I do the subtraction, I'm getting the answer for the definite integral to be pi over 4. Go ahead and write example number 3 in your notes. So we've got the antiderivative of e to the x over 1 minus e to the 2x. Now one thing that's a clue for us, and that I'm not going to do a u substitution here, is that my exponents on my e's are different. If I were to try to let u equal 1 minus e to the 2x, the derivative would be negative 2 e to the 2x, and I don't have that. So instead, I'm going to look at this as an inverse trig function and say that my a squared is equal to 1, so a must be 1. E to the 2x is also a term squared, so that's going to be my u squared. If u squared is equal to e to the 2x, u must be the thing that I'm squaring to get e to the 2x, and that's just e to the x. Remember, when I'm multiplying something by itself, I add the exponents. Now, here's where I've got to watch out for the derivative. So when I take the derivative of e to the x, it's e to the x dx. Lucky for us, we do have that derivative right there. Do you recognize this as our inverse sine again? So this, again, inverse sine does not have a coefficient, so I'm going to say the arc sine of u over a, so e to the x over 1, plus c for my indefinite integral. The number 4 is set up very similarly, so I'm going to say, oh, I'm starting with the number squared, so a squared is equal to 9, so a must be 3. And the second half of this, the variable squared is just x squared, so u must be x, and the derivative of x is just 1 dx, which I do have. So this one is a nice, easy arc sine of u over a plus c. And again, you'll notice that arc sine does not have a coefficient. Now the only difference, you might be wondering how arc secant would look. The only difference for arc secant is that the arc secant radical would start with my variable and then subtract the number, and arc secant would also have to have the variable out in front. Go ahead to our last example. So our last example is the antiderivative of dx over 4 plus 25x squared. So I again see that I've got a plus here, so that's going to tell me arc tangent. So the a squared is equal to 4, so a must be 2. The variable squared, u squared, is equal to 25x squared. So think about what u would have to be. Let's take the square root, and u would have to be equal to 5x. Now this is a really important step here that we haven't seen a whole lot of. The derivative of 5x is 5 dx. But in my original problem, I don't have that 5 dx. So like we've done throughout the whole section on integrals, I'm going to have to multiply by a 5, which puts a 1/5 out in front. So that 1/5 is going to go to my answer. Now watch out here because this is arc tangent, and we know that the form for arc tangent starts with the coefficient 1 over a. So I'm going to have to put a 1 over 2 out in front of that. And then I'm taking the arc tangent of u over a, and again it's an indefinite integral, so it looks like this. Those coefficients out in front would multiply together, so that's giving me 1/10 the arc tangent of 5x over 2 plus c for my final answer. So practice with some of these in your textbook so that you get good at recognizing which inverse trig function we have. And again, notice the difference between doing these inverse trig antiderivatives versus a u substitution. I would always try to do u substitution first, but if the derivative of the u is not present and I can't multiply to get it, then this is a good alternative for some of the problems where u substitution doesn't work. Have a great night, and again, practice with some more of these problems and review for our test next week.